Okay, so here's a structure. It's a cantilever beam with a 5 kip load here in the center. And we want to find the slope and displacement at point B, which is the free end. Now, in our discussion before about cantilever beams, we know that point B is the place where that is maximum displacement and maximum slope. So we're going to use the conjugate beam method. So what's the first thing we need to do for conjugate beam? Draw the moment diagram. So I'm going to shortcut this a little bit and let you know that we're going to have a 5 kip shear at that end, and that our moment will be negative and equal to 75 kip feet. Basically just 15 times 5. I'm sure if you took the time to do your equations of equilibrium, you'd find the same values. So I'm going to just quickly create a little template for us to construct our shear force and bending moment diagram. So there's my positive shear, and all my values will have units of kip. What is the shear at A? Looks like it's 5. There's no change in shear because the air in the load diagram is 0. Slope is 0. So I get a nice constant value of shear of 5 kips. No shear on the second half of the beam. Okay? Any questions about that? So now I'll draw a moment diagram. And this will have units of kips and feet. What's the moment at A? Negative 75. And the change in moment between these 2 points is the area of the shear diagram, which is positive 75. Brings us to 0, and it has a constant positive slope. So there's my moment diagram. Not too bad. So what's next? Conjugate beam. So let's go draw my conjugate beam. Now, in our discussion about conjugate beam, we know how to handle these supports. So a fixed end becomes free in the conjugate beam, and our free end becomes fixed. So when I draw my conjugate beam, it looks like this. Now, what do I apply to that as load? My moment diagram. Now, to help you kind of visualize this, I'm just going to take that moment diagram and I'm just going to plunk it down right over here on the beam. And I know this has a value of 75 kip feet. And of course, part of the conversion to the conjugate beam method is that we divide by EI. Now, what kind of moment is this? Positive or negative? Negative. So what direction is negative load? Down. Now, if this is correct, you just forget about all that. Now you're just working this problem. You've made the conversion from the real beam to the conjugate beam. This is the problem you're working on now. And it's asked you to find the slope and displacement at B. Now remember, positive shear on this side is down. And positive moment is in this direction. So all I have to find are these 2 values for this load. And I know that the shear in the conjugate beam is going to be the slope in the real beam. And the moment in the conjugate beam is going to be the displacement. So I just need to find those reactions and I'm done. So let's start simple. Let's do it. So first of all, I can resolve this force into a concentrated equivalent. I forgot my dimensions here. This is 15 feet and 15 feet. So my load here is going to be 1/2, it's a triangle, the base, which is 15 feet, times the height, which is 75 kip feet, divided by EI. I'm going to need some help with that. What's 75 times 15 divided by 2? $500 and something? What is it? So okay, so 562.5, and that's going to be kip feet squared divided by EI. And now what's the distance from here to here? Well, right here we know is 15. What's this distance here? 2/3 of the distance, which would be another 10. So we have everything we need now. So I'll now sum moments at B, make sure I'm in equilibrium. So I start here. I've got my applied moment, which is positive, moment at B. And my force creates positive moment, right? So I'll start off with plus, and that'll be 562.5 kip feet squared divided by EI, that's the force, times the distance of 25 feet. And that's it. So what's the moment at B? It's whatever 562.5 is divided by multiplied by 25. What's that?
14,062.5.
And that would now be kip feet cubed over EI, plus it's going to be negative when you solve for a moment. Okay? So now, I was actually given a value for E and I, so let's plug those values in here and see what we get. So remember that our moment at B really is a model for the displacement at B, which is now going to be negative, and I'll have my 14,062.5 kip feet cubed, and I want to divide that by E and I. I like to do it this way. I'll put my E here, so that's 30,000 kip inches squared, and I is 800 inches to the fourth, and then I need to convert my cubic feet, so that's 1728 inches cubed in a foot cubed. And if you look carefully, kips cancel, feet cubed cancel. I have inches to the fifth divided by inches to the fourth, which is just an inch. So what do you get? What is all that? That seems pretty reasonable. So at 30 feet, this beam deflects 1 inch down. What about the slope? Well, I can get the slope by doing what? Summing the forces. So sum forces in the y direction. Make sure they're in equilibrium. What do we have? We have the shear force is acting down, and the load is acting down. 562.5, and that's kip feet squared divided by EI. So it looks like the shear at B is negative 562.5 kip feet squared divided by EI. What does negative mean? Negative slope. If I go back to my original beam, I kind of expect this beam to deflect something like that. So you can see I have negative displacement, and what kind of slope is that? Positive or negative? Negative. That matches my number. Now remember that shear in the conjugate beam maps to slope in the real beam. So again, I'll convert this. I've got 562.5 kip feet squared, and let's put all of our values for E and I in. So again, E is 30,000 kips per inch squared. I is 800 inches to the fourth. But now I have feet squared. So that's 12 squared inches. So that's 144 inches squared per feet squared. And if you look at the units again, kips, take out kips, square feet. I have inches to the fourth in the numerator, inches to the fourth in the denominator. It is dimensionless. And mathematically, that's going to come out in radians. So I ran out of room at the bottom, so I'll write it over here. So what is the slope at B? It's going to be a pretty small number, I guess. I'm guessing it's going to be 0.0 something.
Negative 0.0034.
Close enough. And that'll be in radians. Pretty small angle.
You want it in degrees?
Nope.
Jinx, you owe me a Coke.
Who wants a Coke? I can think of something better to drink than that. Any questions about this?
Hey, you know Starbucks has a new kale smoothie?
Yummy.
I thought you'd like that.
I have my own. They probably cost a little bit less than what they cost at Starbucks.
I'm sure it does. It'll probably better.
So any other questions about this? Mr. Woodward.
Yeah, would the curve now actually be a straight line from the midpoint?
Well, I didn't draw it very well. It should have been a curve, and then it should have gone straight here.
Okay.
But the idea is still the same: negative displacement and negative. Yeah, you're right. This second half of the beam is not bending because there's no load on it.
Okay.
So you don't want it in degrees?
I do not want the answer in degrees.
Rad.